Hello and welcome to this part of the SeaSharp Eurocode9 tutorial. This part will be about defining the beams and the properties related to the beams. We start by creating a new workspace. We replace this one. Then we generate a new assembly. Just give it a name. In this case, we call it helideck, since it's a helideck we're going to look at. Then we go into the Eurocode9 beams folder and we say detect Eurocode9 beams from FEM file. And what we will do now is to read in the beams defined in a Genie SeaSharp beam model. And then we just select the FEM file, and here we have option to skip all the smallest beams, which is typically what you will do if you have a lot of small plate stiffener beams that you don't want to include in the code checking. Then you specify a value here like 100 millimeter, and all the beams with height less than this will then be skipped. And then we say OK. And it takes just a little bit of time to read in the beams. And then you see that they have popped up here in the browser, and we can visualize them by pressing here, left mouse button. And while they are being visualized, you just have a quick look at what you see here in the browser. Name, cross-section, the coordinate of the endpoints, and some more information here also. Now zoom. In this model we have some beams that we are not interested in code checking since they are made of steel and not aluminium. So I make a left selection, then I select everything that is intersected by the rectangle, and I say delete, and they are all deleted. Then we can go into the sections folder. Here we have some sections that have been read in from the FEM file. The first thing I will do is just to delete the unused ones belonging to the beams that we have deleted. And now we are left with 5 sections. One of them is a general section. And if we look at the definition of this, we see that there is quite a lot of information missing, like the warping constant and the shear center and so forth. And this information was not present in the FEM file from SeaSharp, so we will have to define it here. But it's impractical to calculate these ones, so what I will do is we will create what's called a general section. General rectangles section. And here we can specify the section type, torsional flexural buckling type is already at the outstands of general, and the weld type, and whether or not the entire section will be heat affected if there is a transverse weld. Then we specify the coordinates of the rectangles making up the section, and now I will just paste them in from this spreadsheet here. I just press Ctrl V to paste, and again we go back and we select the region here, Ctrl C to copy, Ctrl V to paste into this table. And now we see that we have the section rectangles, this simple I section, and when we go through the parts, we see that all the outstanding parts are external, and the web is an internal part. And for the web, we have two heat affected zones at the bottom and at the top. So we specify that here and say that they are heat affected. Part 2, it's this one, which is heat affected. For part 3, it's the entire. Part 4, it's this one. For part 5, 6, 7, it will be like this. For 6, it's the entire, and for 7, it's this rectangle. So now everything should be okay, and we can say okay. Then we have a useful tool which is called create general section from this section, but before we do that we will define a material, new aluminium material, and here we specify some standard properties: yield, ultimate tensile, yield reduction factor in the heat affected zone, and ultimate reduction factor in the heat affected zone, and the buckling class. And to find the buckling class, you have to go into this table in the Eurocode9 standard. And then we just press OK. And we can assign this material immediately. I just select all the beams. Or you can make a sub-selection, of course. But in this case, I just apply the same for all the beams. Apply the property to the selection. And this takes just a little bit of time. So we have to wait for 2 seconds while this one is running. There, it's finished. And then we can go back to the sections and we can say create general section from this section. And what's interesting now is that we can see all the properties that the program has calculated, like the torsion constant, CW, and the coordinates of the shear center, and a bunch of other parameters that are used in the code checking. And if we want to, we can go into this list and define our own values for the properties if we believe that the program did not calculate the correct values. So now we have all this information, and I just say cancel. And then we have another useful tool, which is this one, and it shows how the heat affected zones of the sections actually look for different loading and different heat affection scenarios, like the heat affected zones with the yield reduction. And this will also depend on the force, so we specify a force here, which is just the tension. And then it's update the graph, and it displays how the different parts of the section are heat affected. Okay. And now we wanted to replace this general section from Genie. So we just select all the objects using this. Then we apply this new section. Apply property to selection. And then we have applied this new section to all these small beams. Now there is one more property here related to the beams, and that's the beam type, and that's either truss. If the beam is a truss, you only check the axial forces and not the bending moments or the buckling. And if we right click on all the beams now, we can have a look at how they are defined. We take edit, and we see that you have the endpoints. Also note here that all the edit combo controls have this button on the right side, and if you click this, you go directly into the definition of this object in the combo. and in this case it's a point and just the x, y, and z coordinates of this point. So the beam has two endpoints, and then it has a z-axis transformation. And if you take end one of the beam and transform with this z-axis transformation, then you get a new point, and if you take the vector from end 1 to end 2 and cross it with the vector from end 1 to the transformed point, you get the direction of the local y-axis. So the point that you get when you transform end 1 with the z-axis transformation defines the local xz plane of the beam. And here you just select the cross-section, the material, and the beam type, truss or stiffness for all degrees of freedom. If the beam has an eccentricity, there is a transformation corresponding to the eccentricity of the beam end. And then you have the buckling length factor about the local y and the local z axis of the beam. Just to recap on the axis definition, this is typically how the axes are defined. The x is along the axis of the beam, y in this direction, and z in the direction of the web. So the buckling length factor about local y will be the buckling with the rotation about the local y-axis of the beam endpoints. And similarly, buckling length factor about local z means that the beam is free to rotate about the local z-axis when it buckles. And here you specify the critical buckling mode. This is actually not in use anymore, so it does not matter what you specify here anymore. Then some of the checks, you have to specify whether or not it's a rigid endpoint. To see the definition of that, you have to go into the standard in figure 627. Okay, so that was a quick look at how the beams are defined. And you see the points that the beams are using, they are here. And all the transformations, they use distances. So if I double click on here, you see that this transformation is using 3 different distances for the x, y, and z direction. And the distances are defined here. And that completes the introduction to the definition of the beams. Thank you.